We're now going to look at percent composition for compounds. We have already talked before about how the subscripts, the numbers after the elements, represent how many atoms of that particular element are in the compound. However, what we haven't talked about, but is also true, is it represents the number of moles of that element within the compound. So when we say 13 carbons, we're actually saying there's 13 moles of carbon in this compound for 1 mole of ibuprofen. So to do percent composition, we first need to know what is the total amount in 1 mole. In other words, we need to find the molar mass. So for the carbon, we have 13 moles, and then off the periodic table, 12 grams per mole, and so that'll give us 156 grams of carbon in 1 mole of ibuprofen. Now we have hydrogen. We have 18 moles of hydrogen, and of course they're all at 1 gram per mole, and so we have 18 grams. And then for the oxygen, we have 2 moles times 16 grams per mole, and there we have 32 grams. Now, adding that all together for the carbon and the hydrogen and the oxygen. So carbon, hydrogen, oxygen gives us 206 grams. So molar mass is 206 grams for 1 mole of ibuprofen. Now, we're going to do the same thing in the second example. In the second example, we have a hydrate. A hydrate is when we have a salt, notice the metal and the nonmetals, the salt connected to water molecules. In this case, it's a decahydrate, and deca for the 10. It doesn't have to be deca, it can be any number. And so I just want to show you doing molar mass for a hydrate. So first the salt, we have sodium, carbon, and oxygen, and again 2 moles. That one's times 23 grams per mole. So we have 46 grams of sodium in every 1 mole of this compound. Carbon, there's only 1 carbon, so 1 mole times 12 grams per mole, and so 12 grams. And then the oxygen, we have 3 moles and 16 grams for each one of those, and so 48 grams here. So that gives us a total for the salt, Na2CO3 will be 46 grams plus the 12 plus the 48 grams, so 106 grams for 1 mole of the Na2CO3. Now, what about the water? Well, in the water, H2O, we've done H2O before. There are 18 grams per mole. We have 10 of these. So that's going to be 10 times the 18 grams per mole. And so in this case we have 180 grams of H2O per 1 mole of this hydrate. Putting the two together for Na2CO3 and then the decahydrate part, well, that's going to be 106 plus 180, and therefore 286 grams per 1 mole. So, things we have done before, little twist on the hydrate, but this is how you find the molar mass of a compound. Now, mass percentage, or percentage in general, is always the part out of the whole times 100%, or times 100. And so here we've been doing what are the wholes, and now we're going to look at what are the mass percentages of some parts of those. So first, the oxygen. If we look at the oxygen from problem 1, we see that we had 32 grams of oxygen in 1 mole of ibuprofen. The total was 206 grams, and then times 100%. And so basically 15.5% of oxygen in the ibuprofen. So what that means is no matter how much ibuprofen we have, if we want to know how much oxygen is in it, then it's going to be 15.5% of that total. So if we had 100 grams, it'd be 15.5. If we had 200 grams, then it would, of ibuprofen, then it would be 31 grams of oxygen in that 200 grams of ibuprofen. Now, we also have, what about the water in the decahydrate? And so again, for H2O, that's the piece that we're focused on. We're going to look at the water. Well, that was 180 grams. The total was 286 grams, and then times 100. And so we're going to get almost 63% water in this decahydrate, sodium carbonate decahydrate. I'd like to also mention that even though this is a dot for the hydrate, it does not mean multiply. We found this part here and then 10 of waters and added the two together. So that's really the idea behind a percent composition. We have found the part, the oxygen in the first case, the water in the second case, out of the total. Now, let's suppose that in a different problem, we have what is the percent composition of Cu2S, copper 1 sulfide. By the way, copper 1 tells us that the copper had a +1 charge. Sulfur in the same column as oxygen has a -2 charge, so we needed 2 coppers to do that. Now in this case it doesn't seem to specify, so anytime you see this kind of question, what is the percent composition of a compound, then what the question is really asking is what is the percentage for every element that's in the compound. And in this case we have 2 of them. So first, like previously, we need to find the total for this compound. We need to find the molar mass. And so copper, we can round that off to 64 grams per mole. So basically we have 2 moles of copper. And then, as I said, 64 grams per mole. Plus, we have just 1 sulfur. And that's 32 grams per mole. and this one's for the sulfur. And so this would be 128 grams, plus this one will give us 32 more. And so 160 grams for the molar mass of Cu2S. So now we have the total, and we can find each of the percent compositions. So let's do the copper first, and then the sulfur. Copper, 128 grams divided by the 160 times 100%, and we have 80% copper. Okay, now the other one, 32 grams divided by the 160, and again times 100, and we have 20% sulfur. And of course, when we get done, if we add those up, 20% and 80% should give us 100%. In other words, we should have the whole thing there when we add out all the percentages. And of course, what we could have done for the sulfur is we could have simply said, hey, 100% subtract the 80% that was the copper, and we could get our 20% that way as well. So we don't necessarily have to do the division and percentage for each individual one. We just have to do all but one, and then we can subtract out for what's remaining. So the percent composition of Cu2S, 80% copper and 20% sulfur. And again, the point of the percent composition is it doesn't matter how much we have. So if I had 500 grams of this stuff, 80% of it would be copper. And if I had 10 grams, again, 80% of it would be copper, and the other 20% would be sulfur. Now, in the next one, we don't actually have a formula, and that's actually the direction that we're moving in with this work, which is, we can have compounds, we can actually have the physical material in front of us, and we can know how much of each thing is, but we want to kind of work towards, what's the compound when we have so much of one thing and so much of another thing. And so in this case, we have the total, the 12 grams, and we have how much copper that is and how much sulfur that is, and so we can figure out the percent compositions of those, because again, we have a part and we have a total. So for the copper part here, we're going to have 7.96 grams divided by the 12 grams, and then times 100. And get out our calculator. 7.96 divided by 12 times 100. And this one comes out to be 66.3%. The threes would continue on. All right, now for the other one, we're just going to go ahead and do this the long way. For the sulfur, we have 4.04 grams divided by the 12 grams times the 100. And so 4.04 divided by the 12, and this one comes out basically 33.7%. This one has sixes that continue, so I've rounded in the tenths place. And again, I could have just subtracted in the first place, but it's kind of a nice way of checking. Add the two together, and in fact, I have 100% here. Now, the thing to notice is in number 4, it was 80% copper and 20% sulfur, and here in number 5, it is about 2/3 copper. 66.7 would be 2/3, 66.3% copper, and 33.7% sulfur. And this is more on the matter of a 2-to-1 kind of ratio. This one was 4-to-1. This one will lead us to a different formula for our compound than this one did. I believe, let me just double check. If instead of this being copper 1 sulfide, it's copper 2 sulfide, which means its charge would be a +2, and again, sulfur is always -2. Put those two together, it would be CuS, and 1 copper, of course that's 64 grams, similar to what we did up there, plus 1 sulfur, 32 grams, like we did up there, and so that gives us 96 grams for 1 mole. But at the same time, we can see that the 64 out of the 96 times 100 gives me basically 66.7%, and the 32 out of the 96 grams times 100 gives me 33.3%. And so there's that same 2-to-1 ratio that we got in the mounts. Now, we're off a little bit, but that's probably just a rounding amount depending on how many decimal places that you wanted to go for. But the bottom line is the actual physical amounts in grams of each of the elements will lead us back to what the compound formula will look like. Each different formula for the same elements will have different percent compositions. And so in the next lesson we will find out how to go from the percentages to figure out what the formula will be. Now in this last question we're kind of work towards, all right, let's suppose I have 150 grams of calcium hydroxide and I want to know how much in mass is that of calcium. So this is similar to what we've been doing so far, percent compositions, but then we're going to kind of do an extra step to find out how much that would be of the calcium in this case. So first off, for the calcium, I got calcium, oxygen, and hydrogen. Remember that the subscript, a 2 outside of parentheses, means everything inside is, in this case, doubled. So calcium, I have just 1 mole because there's no subscript right here. So 1 mole times 40 grams per mole. So I have 40 grams of this stuff. The oxygen, 2 moles times 16 grams per 1 mole. And so 32 grams. And then the hydrogen, 2 moles, 1 gram per mole. And so I have 2 grams. And add those all together, and I have 74 grams per 1 mole of the Ca calcium hydroxide, CaOH2. Now, if we find the percent composition of the calcium, because that's what we're interested in, so that'll be 40 grams divided by the 74 grams times 100%. So 40 divided by 74 times 100 is basically 54.1% calcium, just like we did in the previous problems. And so now here comes our extra step. We have 150 grams of this stuff, calcium hydroxide. How much of that is in grams? So anytime you see mass, okay, anytime you see mass, remember that's grams. So how much of that in grams is actually the calcium. And so I just take my 150 grams times. Now, when I'm doing the math, I don't write it as a percentage. I write it as a decimal. So note how I've moved the decimal place over twice. So 54.1% became 0.541. And so take that 0.541 times 150, and basically 81.1 grams of calcium in 150 grams of the CaOH2. And so knowing the formula and knowing the percentage, I can then find out how many grams of any piece, in this case the calcium, that I want to know. And so in every 150 grams of calcium hydroxide, we should have 81.1 grams of calcium. So that's it for percent composition. The next time we will go and look at empirical formulas.